So, welcome once again, lecture 5 in our 13 lecture encounter. We have another exciting day in front of us. We are going to learn a tool which I'm sure many of you will have seen before, generally speaking, the hypothesis test tool. The tool which is sometimes a bit unfortunate actually, being put as kind of the definition of what statistics really is. And I will share with you, it's a very good tool that we can use for many things, but it's not synonymous with the concept of learning from data. It's one of several tools to learn from data, but not the only one. That's the topic of this afternoon. So to begin, I give you an example with the result basically in the beginning, as usual, and then we look into it, how we get there. That's the first part. We will recap the confidence interval as we go along, because these two things, hypothesis test, confidence intervals, they sort of go hand in hand. And then we are going to have an additional thing at the end, talking about checking for normality and potentially transforming data if we think it is needed. So, motivating example. Let's look at this little story. The question is whether some two different sleeping medicines, whether we have any difference. So we are a sleeping medicine producing company, say. And we have two options to go for. And we'd like to test those two options. Or we test our product prototype with a competitor's prototype, for instance. That's another situation. We have two kinds of sleeping medicine, A and B. We are having 10 test persons, trying both of them, because that can be done with sleeping medicine. You can have one person try one and then relax for a week or two and then get the other medication and try that one, right? So you can do so-called crossover studies in this framework. What we record here is a single thing for each person. We measure the difference between the two sleeping medicine effects. So, for instance, for person 1, the B medicine was 1.2 hours better than the A medicine. Let's not get into detail of what happened behind those 1.2 hours, but let's just assume that's the way we measure this thing. It's 1.2 hours for person 1, 2.4 hours for person 2, and so on. What is your gut feeling about the conclusion, about what is actually to learn from these data about the sleeping medicines by just looking at those numbers? That's a good place to start always. Yes? It looks like the B is more effective is the answer, and I would be inclined to agree with you. Because for all 10 persons, it seems that they have a plus effect of the B. Good observation. So basically maybe the result is already there, but let's try to see how we would formalize the so-called hypothesis test approach for making that conclusion. Now, this is the way it would usually be put in a scientific context. This is related to the whole way of scientific reasoning and thinking, what we are talking about here. What we would do here is to put up the so-called null hypothesis, the hypothesis of no difference. That hypothesis could mathematically be expressed like this, where some mean, mu, of something, in this case for the difference of effects, of course, right? For the difference of the two effects. Such a mean is hypothesized to be 0. We do that when we have the aim and the wish and the hope that we would be able to prove it to be non-zero. When we want to prove something is non-zero, that there is an effect, we put up the sort of the opposite null hypothesis to be able to sort of reject or come with evidence against the null. That's how we collect as good proof as possible that we found something new. So the idea is we want to find something new, make a proof of something, that new insight. So we need to come up with some evidence against some null. That's the way we talk about it. Well, computationally, we are basically stuck in the same situation here. So that shouldn't be too complicated to us, because it's just one-column data. We could already compute the mean and the sample standard deviations of these numbers, and we have also learned to consider those as estimates of unknown mean effect and unknown variability of effects, of difference of effects. Then the question we give ourselves is the following. Would our data be in accordance with the null hypothesis, right? We hypothesize here a 0 effect. We look at the data. The data comes out as on average. It turns out here, the average here is 1.67, if I take the average of these 10 numbers. What any one of us would do, I would say from around mid-elementary school age, if we were asked this question, we would look at this number and we would compare it with this number, I would say, in our minds. Could we prove there is an effect? Well, I see on average there is a 1 hour 67 minutes, 1 hour, sorry, 0.67, 1 hour 40 minutes effect, of course. So it looks like if there is an effect, right? The number tells me there seems to be something going on. It's definitely not 0. So the data is not 0, so maybe there is an effect. The only thing is, can we be sure? Or how sure can we be? Is because data will vary, right? Whenever I do a study with 10 patients and do such a study, I will never get a 0, right? I will get some number. The average will be either positive or negative. It will be a number. The question is this observed number far enough away from 0 to allow us to claim that we believe we have an important finding, right? That's the thinking here. That's the new thing. We're going to put this evaluation, because this is where the randomness comes in, right? A mean is random from sample to sample. So it's going to be random whether we're at 0 or not. And we are going to use probability to qualify this line of thinking, this line of making decisions. Because we are going to learn about the p-value. And we are going to learn that if we evaluate how far away from 0 that this number is in this case, in a way, that number is this away from 0, or if I may be more specific, which I will be, it is pretty unlikely, this p-value, which I will teach you now within the next hour, right? The p-value states that it's pretty unlikely to be so far away, because this probability is computed under a scenario-based thinking. What if the null was true? That's the kind of the scenario I put in myself. Could I see 1.67 hour just by chance? In case the null is true, that's the probability I'm finding. Could it be that it could very well be 0, but then this deviance from 0 is a pretty expected deviance, or pretty expected effect to see? This probability, in my personal little perspective, that's a pretty low probability, 1 out of 1,000. It will only happen 1 out of 1,000 times I do such an experiment, with truly no difference of the medicines, that I would see such a large discrepancy between the 0 and the data. What will that make me conclude? That will make me conclude that I don't believe in the null. I have proved the null wrong. I have provided evidence against the null. So I have proven the so-called significant effect of sleeping medicine A compared to B. I look at the number, I see A is larger than B, so that's my conclusion. B larger than A, if I said it opposite, it's B that has the larger effect. Thank you. I saw you did that with your fingers, but still I thought I said it the right way, but probably you're right. I could see it in the other eyes also. That's basically what we are going to be taught today. Hypothesis testing and p-values for the first time. And then for the rest of the course, we will have this duality play between hypothesis tests, p-values, confidence intervals for all sorts of different situations that will prepare you a little bit more for the world that will hit you after this course. Before we jump onto it, I would like to share with you, I don't know if I actually had previously had so much time to show you these links. There are a number of beautiful stories that I've linked to in the CampusNet group, or the Insight DTU group as it's called now. I added 3 new links at the bottom here, 2 of them in Danish, 1 in English. It's just because these links that I added just before coming here are very closely related to the topic of hypothesis testing. And if you start Googling hypothesis testing, p-values, you will find a global confusion and global disagreement and global discussion about pros and cons of hypothesis testing and p-values. Well, we are here to help the global confusion. That's part of university business. So what we did was, the interesting thing was this link, that even though we've been doing hypothesis testing and confidence intervals for a bit more than 100 years now, for the first time in the ASA, American Statistical Association's history, they found it useful and necessary to make a press release about talking about methodology. They never before made a press release talking about methodology. Methodology was part of the research community and part of the research journals. And this March 2016, less than 1 year ago, is about statement on statistical significance and p-values. Just to, this is something that is being discussed at the highest scientific grounds, actually. It is warning a little bit, and if you read it simple-mindedly, you might read it as if we shouldn't do hypothesis testing and p-values. Well, if you read more carefully, that's not what it's saying. It's saying, don't bet your life on only a p-value, right? Don't bet your company's life. Don't bet your scientific decisions on just a p-value. Use a little bit more intelligence than just looking at one p-value. That's my version of what's in this document. What it says more is, look very much on confidence intervals also. Don't only you'll look at p-values. Now, what we then that took me and a colleague of mine, the current chairman of the Danish Statistical Society, DSTS, that I was chairing myself a few years back, to make a little note in what is known as Aktuel Naturvidenskab in Danish. I realize some of you don't read this. It's just to say that basically what we're saying in Danish here, well, this is great news, but we knew that for 100 years already. But we agree about the message of the ASA. Of course, that's good. We've told that in our stats classes, and our ancestors told that 50 years ago. But maybe something has happened in the world. Maybe this has been misused a little bit out there. So it's good news that the ASA is helping us to make that point again. So if you're Danish speaking, you can read this little note. Then actually I just wanted to share with you the last one here. This is Klaus, who was co-authoring the other one. He has his own little blog. He sits in the evenings and shares really nice inputs and goodies about probability and stats. So please, this is a Danish, is the number of Nicolas Cage movies related to drinking. That's the one thing, and yeah. statistics in high school, and then who's going to win the European Championships 2016? Is it really true? And then also in Danish again, there's this story about p-values, a joint blog with Klaus and myself. A really interesting place to go to become vis or wise, which is the Danish word for wise, V-I-S. That was my introduction to what we're going to do today.